see Lindelof videos, analysis of a rational function. A lot of times, well, not a lot of times, every time when you're analyzing a rational function, you want to talk about end behavior, and often that behavior is asymptotic. That is to say that at the end, the function starts to approach a certain height that we can generalize. In this case, that's not as true, so this is kind of weird. This goes from Theorem of horizontal asymptotes, which says that when we look, what we really want to do is look at this. We want to look at the lead variables, that is the variables in the numerator and the denominator that have the highest exponential values. And then you want to compare those values. So we have x to the fourth up here and x to the third here. Well, when you look at that, what you're supposed to be able to see from this is that the top is going to grow a lot faster than the bottom, so we're going to have this kind of unbounded behavior. So when we look at this relationship and we see this, some people call this improper, this fraction improper. It's actually not, but that's what they consider it. When I see this, when I compare the lead variables, and I see that this value, this exponential value, is higher than this one, I know that we have an oblique asymptote, and that is that the function's end behavior is going to approach or start to look like or resemble the behavior of some other function. In this case, I think it's a line. So this is what we have to do here. When we get to this, as soon as you see this in your analysis, then what you need to do is start this actual division process, and it's this top piece divided by the bottom piece. So we have x cubed minus x squared plus 1, and we're going to divide that into 3x to the fourth minus 0x cubed minus x squared plus or minus 0 x's plus or minus 0, doesn't matter. You'll see in a second why I'm showing all of this crap here. So now I'm going to start that division process, and as I do this polynomial division, I'm just going to do this. 3x to the fourth divided by x cubed is 3x, isn't it? And then now what I'm going to do is I'm going to multiply here, here, and here, and get 3x to the fourth. 3x times x cubed is 3x to the fourth. 3x times negative x squared is negative 3x cubed, isn't it? 3x times 1 is positive 3x's. And look, I'm holding these places here. Otherwise, I might have put this 3x in here, and it leads to a hell of a lot of confusion. Then remember from there that we're going to be subtracting the whole lot. So all these signs change. So this goes to negative, this goes to positive, this goes to negative. So we do this subtraction, we get nothing here. We get 3x cubed. We bring down this negative x squared, and this comes down as negative 3x. Guess what we're going to do next? Well, we're going to start that division process again. Now, this time, we are going to divide 3x cubed by x cubed, which gives us 3, so positive 3. To prove that, 3 times x cubed is 3x cubed. 3 times negative x squared is negative 3x squared, isn't it? And 3 times 1 is 1 out here. Do you see where these place values are coming in handy here? We're going to subtract the whole thing out, so all the signs will change. This becomes a negative, this becomes positive, this becomes negative. This goes to 0. 3x squared minus x squared is 2x squared, isn't it? The negative 3x comes down because there was 0, so 3x minus 1. This gets to be kind of the weird part, but I do want to show it to you. So what we can say about this is that our function can be rewritten as f of x is equal to 3x plus 3 plus its remainder, and this is the remainder right here, isn't it? This is its remainder, so it's 2x squared minus 3x minus 1 all over x cubed minus x squared plus 1. So this is what we can say here. We can say that our oblique asymptote is this piece right here. So our oblique asymptote is this piece right here. Because as the limit, remember, we're looking for asymptotic behavior, end behavior, and the end behavior of this is 0. as numbers get enormously large, you have something squared over something cubed, the cubed is going to grow so much faster that this value is going to approach 0. So our oblique asymptote is y is equal to 3x plus 3. Let me show you what that actually looks like, because it's bothersome. Here's the function that we were just talking about. Now look at this for a second. If I go back in here and I put in that 3x plus 3, 3x plus 3, hopefully you can see that the end behavior of this, as x goes to negative infinity, these two functions run really close together, don't they? And if we could look at it the other way, you can see what this function does. Can you see how they closely resemble each other? And when you're looking for an asymptote, you're looking for end behavior. So I hope this was helpful. It's really pretty difficult stuff. Thanks for watching. If you have any questions or comments, please let me know.